Similar. They are similar, okay? And they're similar by angle, correct?
Yeah. Yes.
All right, because we can find the missing angles and see that they indeed are all congruent, okay? So, question 2, are those similar?
Yeah.
Yes, this angle here would be 59, right? This one would be 61, so you got 3 angles congruent to 3 angles. That meets angle. What about the number 3? Similar, okay? If you're struggling with these types of questions, know that angle is in both triangles, correct?
Yeah.
Okay. So you got one angle congruent to one angle, and then that angle there and that angle there are corresponding, aren't they? And they're created by parallel lines. So with parallel lines being cut by transversals, corresponding angles are congruent. So those 2 triangles, the small one here, okay, and then the overall one are similar by angle. What about these 2?
Similar.
Okay. We have, yeah, you're right.
Yeah.
We have 42 here. Okay. So we have 138 degrees left over for these 2 angles, right?
Well, I know because lines.
Okay, so these are congruent, right? But the idea is, so you know that this angle here is congruent to that angle there, right? Everybody okay with that? This angle here is congruent to that angle there. So we know it's 138 over 2 and 138 over 2. Okay? That's not enough, though, to say that these are similar. We need to be able to compare angles from this triangle over to this triangle. So is this angle here also 138 over 2?
Yeah.
Yeah. So now we have an angle over here congruent to an angle over here. 42 congruent to 42. We have angle.
Can you just say 138 divided by 2?
Yeah, that's what I did.
Good. Well, you put it over 2, so I didn't know if you guys wanted decimal.
If I look at
Similar.
these 2, are they similar?
Similar.
Well, if they are similar, you have to be able to tell me one of 2 things. You have to be able to go through and show me that you have angles congruent to angles, 2 angles congruent to 2 angles. And here's the argument. Would this angle here be congruent to that angle there?
Yes.
All right, but is there anything telling me that they're going to be congruent over here?
Yes.
Is that angle there going to be congruent to that angle there?
Yes.
Yes, so we know that, right? But is this angle here ever going to be congruent to that one? Or always congruent to that one?
Yeah, no, not always.
Not always, and that's the issue. Okay, not always.
You freaking leave.
So stop.
Sorry.
So, giving you an image here of what we've got going on. These are the 2 kind of triangles of 5 and 5, right? Okay, both sides being 5. But if we look at this, we don't have, there's so many different triangles that can be created. And if we're going to have angle, that means that this angle up here needs to be congruent to that angle there, right? Because if I have angle, what do I really have? Don't I really have angle? So that means when angle exists, I should actually have 3 pairs of congruent angles. That means if these 2 things are similar, this angle here should be congruent to that one, and they're not. Okay? So that means these other 2 cannot be congruent, and I don't have angle. Now, it could happen. I could make that case there. Okay? Now, I'm off a little bit, but if I was able to make that 44.62, that 44.62, these would be similar. Does that make sense? Now, a scale factor to them would be 1, so there's a better word than similar for that. Okay, if I have a scale factor that's 1, does anybody know what those shapes would be? Congruent. Okay, so it could happen, but in general, with the information provided, I do not know. So we say no conclusion. And when you come up with no conclusion, it doesn't mean that they're not similar. You just don't know whether they're similar or not. Does that make sense? We do the same thing when we talk about congruence. If we said 2 things are not congruent, that's saying that we have declared that there are components that are corresponding that do not share the same angle measurements and do not share the same distances. But if I say I don't know them to be congruent, that means they could be congruent if we knew some more information, but we're not setting a precedent saying we know for certain that these things are not similar because they could be. We just don't have the information to say they are. Does that make sense? Okay. I could say, Johnny's a B student, and I don't have any grades, okay? Or he's going to finish the 9 weeks with a B, okay? I wouldn't want to say that because there's so many grades yet to be taken, right? There's things out there that we don't know to make the conclusion that he's a B student, okay? Or he's going to be a B student. So those are things to kind of think about when we make that argument of no conclusion. What about question 6? Are those two similar?
I don't understand that. I put similar, but...
Okay, they are similar, and here's my question. Should we be looking at this shape here? No, that's a quadrilateral, isn't it?
Yeah.
Okay, so and that's what a lot of people wanted to look at, and they wanted to compare that shape to one of the triangles. You can't do that. Would you agree that that triangle right there has a right angle in it?
Yeah.
Okay. Does the biggest triangle up there have a right angle in it?
Yeah.
So you got an angle congruent to an angle, right? Would you agree that both those triangles share that angle?
Yeah.
So that's another angle congruent to itself, right? That's the reflexive property. So do you have two angles of this triangle congruent to two angles of the big triangle? So those would be similar. Okay. Let's see. What about 7?
I figured since it was just like a triangle size and that triangle would have to be similar.
What are you talking about?
I'm similar to it. For number 6, I just made it. I said yes because I thought since it was inside a triangle, it would have to be.
You just gotta be careful with that because
two angles are the same.
yeah, we got to have those components because I could put that line right there and I got another triangle inside here, right?
Okay.
And that triangle may or may not be similar to the overall one. Okay. The fact that this is a right angle here is really what allows us to do that. If I were to come down here and do this with a right angle, they'd be similar. Okay, and I can actually move that line kind of anywhere I want to as long as I develop a triangle, they would be similar. 7, similar, right? That's kind of maybe one of the easier ones on here. Number 8, I asked you to first look at the gray triangles. And this is a trapezoid. It's important that we have to understand that this is a trapezoid. Now, it may look isosceles, but we don't know that, right? They're not telling us that information. So if this is just a general trapezoid, by definition, what does that tell you about that segment there compared to that one? Yeah, they're parallel. And then this is a what?
Bisector.
Careful. For the parallel lines, it's a...
Segment.
Okay, it's going to create alternate interior angles, but it...
A diagonal.
No. Did you say it, Faith? What'd you say? Transversal. Okay. And that creates those two angles there to be congruent, right? Okay. Alternate interior angles are congruent if the transversal intersects parallel lines. Would you guys agree? I think this is the next set of angles that are kind of the easiest to look at. Would you agree that those two angles there are vertical?
Yeah.
All right, so the red angles and the blue angles are congruent. And we also have the ability to eventually say, because by looking at another transversal, another diagonal, that angle there is going to be congruent to that one there. Okay, so we do have angle existing in here. The gray ones are similar. Does that make sense? Yeah. Gray ones are similar by angle. Now I asked you about the white ones. And you know the white ones, that those are congruent angles, right? So there's an angle for so far. We need one more set of angles. And just going to answer this question quickly for us, I guess, we don't know anything about that angle compared to that angle.
Yeah, because it's parallel.
Well, careful. Are those angles created by the parallel lines?
Yeah. Parallel line helps.
Okay, that angle right there is not created by any of those blue lines, right? The complete angle. And for the same reason, if I looked at that line there, and that line there, we do now have a transversal for those two to create that angle there and that angle there, right? But are these lines parallel?
No, we don't know that.
No. Okay. And actually, we know that they're not parallel
Yeah.
because of the trapezoid. Because we by definition, those cannot be parallel for a trapezoid. So we don't know right now whether that is congruent to that. Okay. And we don't know. So your other option is, well, could that angle there be congruent to that angle there? And off of looks, what would be the argument?
Yes.
Yes. Okay. Because this trapezoid looks isosceles, doesn't it? Okay. But we shouldn't go off of looks. So really, when we look at the white triangles, we should say no conclusion. But if I added this word here, and I told you have an isosceles triangle, you, by all means, can say the white ones are similar, and so are the gray ones. And this is the reason. In an isosceles trapezoid, what did you know about these base angles?
They're the same.
They're the same. And you already told me, based on the parallel lines in the transversal, that angle there was the same as that angle there, right? So if I remove the red stuff from the blue angles, aren't you left with that angle there and that angle there to equate to one another? So you do have now those angles congruent. You got these vertical ones. So if it is isosceles, you do get two sets of similar triangles. If it's not isosceles, you don't. You get one set. Okay. But the argument is for the white ones for our question, because we don't know anything about this trapezoid other than this trapezoid, is that we write no conclusion for the white ones. Okay. If I said if it's trapezoid that is not isosceles, then you can say we know for certain that the white ones are not similar. Okay. Question 9, I think, is the one that, well, you got situations where they could be similar. Let me show you what can happen here. I just created that picture with just some known values in GeoGebra. And right now, I believe these are, I guess, what I had. These two were congruent shapes. But let me just kind of enlarge this one. Do they both have a 120-degree angle?
Yes.
Do they both have a 32.33-degree angle?
Yes.
Okay. So are those triangles for this parallelogram, are those triangles similar?
Yes.
Yes. So we have a situation where they're similar. Okay. Now here's what could happen. Do you still have a triangle over here that's on a 120-degree angle?
Yes.
Do you have a triangle over here that's on a 120-degree angle?
Yes.
But are they similar? Are the remaining angles the same? No. So 16.22 is different than 32.33. So we don't have angle here.
So on my thing, like there's like a part of it that's really dark.
Yeah.
That looks like the same.
Okay, so some people have been saying that's that, and I think the reason for that is I copied this out of a textbook, and I think it's kind of a ghosting image of the page on the back. I don't think they're trying to say that angle there is congruent to that angle there. But if you did say that, if that's the way you interpreted it, and you said that these two things are similar by angle, then you are 100% correct. Okay? So based on the way you interpreted the picture and what the information trying to feed you, we either come up with no conclusion or we come up with angle. Okay? If you do come up with angle, though, I need to know why. And you're telling me that you think they're telling you those two angles are congruent. But that, I think what they're trying to get here is the idea of if I have basically two parallelograms that share the same angle measurements, okay? So 120, that's going to be 60 over here and 60 over here. It does not mean that those triangles that are created by the diagonals are automatically similar, okay? And that's what we're seeing here with these two pictures. Question 10, they ask you to kind of walk yourself through the process that we go through kind of every single time we want to deal with triangle similarity questions or just polygon similarity questions in general. So they were asking you to say, on this question mark, we wanted to put triangle MLN. Here we wanted to write ML. Here we wanted to write MN. and here we want to write LN. Okay, so that's going through the comparison of parts here, creating the three ratios that we're going to then substitute those distances in to find these ratios down here. So 15 over what? 15 over 20. And then it should be 18 over X. 15 over 20, 12 over Y.
Y.
Okay. So that's what we've been doing to create these proportions, so we cross multiply, solve for X, right? What'd you guys get for X? 24, good. And then you would cross multiply that one to solve for Y, and you get 16. Okay. So that's nice because that sets you up, and a lot of worksheets do this. It's kind of a learning thing. They're showing you these are the four things that get you the answer in this question. So those should be the similar four steps that are going to get you the answers down here. What did you guys get for X on number 11? 6. And what's Y?
4.
4. What about 12? What'd you get for X?
9.
9. And Y should be?
I don't think I set it up for
6.
Okay.
13, what'd you get for X?
9.
9
13,
and
9 for X, 4 for Y.
Careful. 5 for Y. Do we want to do a couple of those?
Yeah, because I don't know if I set them up right.
All right, I want to do 12. Let's do 12. Is that okay? Or do you want, is there?
Let's do 12. I didn't understand how to get X.
Okay. So let me cut this out.
6 times 6 divided by 4. 6 times 6. 6 divided by 4.
All right, would you guys agree that that top angle is the same in both triangles? Okay, so that one's compared to that one. And now they're telling you, this angle here is this one. And this angle here is this one. So do you have angle here?
Yeah.
All right, so what would this distance here be in that small triangle?
8. 6.
Careful. Small triangle.
4.
That's 4, right? So I'm going to pick the 4 off, the 6 off, and the Y, right? Does that make sense?
Yeah.
All right, now I need to come over here to the big triangle and do the same thing. So what would this length here be?
6.
6. What would this length over here be?
Y.
Y plus 3.
That's where I would call it.
All right, so we're doing segment addition. All right. Then the bottom is going to be X, right? All right, so now that because the triangles are in the same orientation to one another, meaning that, if I call this one A, B, C, and this one X, Y, Z, angle A is the top angle, angle X is the top angle, they're both congruent, right? B is the lower left, Y is the lower left, they're the ones that are congruent. C is the lower right, Z is the lower right, they're the ones that are congruent. Because they're the same orientation, they're just basically essentially a slide and then a dilation of one another. So I could take this picture here on the left and just slide it over, maybe. Slide it over to become the picture on the right, correct? Whenever you have just a pure translation like that, a slide, you can say left segment to left segment. So would you say 4 to 6?
Yeah.
You can say right segment to right segment. So Y to Y plus 3. And then you can say bottom to bottom, right? So you said 6 to X then, correct?
Oh, I didn't think you put them all 3 on there.
Yeah, all 3 of them are going to be equal.
Okay. 2 at a time.
So then that allows you, once you pick out all 3 of them are equal. Now you can't do any algebra with all 3 of them at the same time. You then have to pick 2 of them to do the work with 2 of them. So maybe you pick those 2 first. Would that allow you to solve for Y?
Yeah.
Yep. Maybe you then take
They picked 2 outside ones.
the 2 outside ones,
I did that.
and that will allow you to solve for X, right? Okay. So that's kind of the approach that you want to use. And you would do the same thing for 11 and 13. Those are all very similar questions there. 11, 12, and 13 for finding x and y. All right. Usually it's not an issue of people using the proportions once you have them, or using the correct ratios to create a proportion. It's usually, comparing the 4 and the 6, the y and the y plus 3. You'd be able to develop that first. And then most people realize, pick 2 of them out and solve. Is that all right?
That's all I do. Well, I did 3 Y. So that's right.
Okay. All right. Number 14. Probably didn't really enjoy this question, did you?
No.
Okay. And I want to go over 14 because it's going to be, I forget what section it is. It might actually be a couple sections in this chapter that provide us some formulas, essentially, that come from theorems about this type of triangle. And what this is, ABC, the overall triangle is a right triangle, correct?
Yes.
Okay. And does anybody remember what kind of segment, and this came from chapter 4, what kind of segment we have right here when we go from a vertex to the side opposite? We're going to be perpendicular. Good. It's an altitude. Okay. So when we have that altitude drawn inside a right triangle like this, there are some relationships that exist. And one of the relationships that exists always, no matter what right triangle you're dealing with, is the fact that 3 triangles get developed, and those 3 triangles are all similar to one another. Okay. Now, when we talk about them as being similar, there is kind of a notation thing we got to pay attention to, an understanding we got to pay attention to. But the reason I want to show this and talk about this is because when we look at this problem, it's going to be very complex for us to work with and solve for x and y. But that should help us gain an appreciation for the theorems that we're going to learn in a couple days that provide us a very effective shortcut to finding x and y. Okay. So here's the thing. We've got, would you guys agree there's 3 triangles up there, right? We've got the overall triangle, which is ABC.
2 triangles in there.
And then I got the 2 smaller ones being broken up, right? So all I've done is I've just kind of redrawn those, the larger triangle, and then redrawn the smaller triangle on the left here, where this would be A, C, and D, right? Which angle do both of those triangles share? Careful. They share the letter C, but up here,
it's B.
In the triangle on the left, C is that angle right there, right? On the triangle on the right, that is C. Does that make sense? Okay. So we're not sharing all of C. What angle do we know for certain we're sharing all of? A. That angle right there is completely overlapped right there, right? If I pull this one over, you see how A matches up, right?
Yeah.
But all of the C up here and all of the C in the other one up top, they are not completely shared, right? Okay. But I need to know that. I need to be able to compare which angles are congruent because I want to write a similarity statement. I want to say triangle, let's just go ABC, is similar
ACD.
to triangle A.
Oh, CD.
Well, I went A, B, C, and then you said what?
ACD.
It should be ACD. Because look at this. A is congruent to A, right? This is your right angle, correct? This is your right angle. Don't they have to be congruent? So don't they have to be in the same location? All right, so you said ACD first, right?
Yeah.
And you were right, and then you backtracked from that. So those 2 things are similar, okay? And that is going to create, eventually, and I'm just going to put the parts here for them, that will eventually create 3 true ratios, correct?
Yes.
Okay. And we'll come back and write those ratios here in a little bit. Now, can I look at, let's see here. doesn't want to copy. There we go. Can I look at that triangle again, the overall triangle, and now compare it to this one on the right? So let's deal with the one on the right here. Let me draw that one out. All right, so the triangle on the right would be C, this would be D, and this would be B, right? D is my right angle. Now, which angle do these two triangles share completely? B. See how B overlaps completely? Okay. So B is congruent to B, and they both have a right angle again, right? So the right angles are your second angle for angle. So now if I name this triangle here ABC, similar to now this triangle over here, if I go A, what do I have to start with over here?
C.
C. They're the unmarked angles, right?
Yeah.
And then I went to B, so that's how I go to
B.
B, and then finish where?
C.
Careful.
D.
D. So we got those two things. Okay. Now, that's going to create three ratios that we could use, right? Okay, we'll come back and write those in a moment. Now here's my question. If you know that ABC is similar to ACD, but ABC is also similar to CBD, what can you tell me about that one and that one? Nope. You're close. They're similar. Okay. There may be a special case where they're congruent. That special case, I believe, is when the original one becomes a 45, 45, 90 right triangle, an isosceles right triangle. But these two triangles, triangle ACD, is going to be similar to triangle CBD as well. So does that create then three more ratios we could develop? So what I want you to understand is that the transitive property exists for similarity in regards to polygons. Okay? Because that's what we're using there to come up with the conclusion that ACD is similar to CBD. Okay? So that being said, let's
I don't like when homework is on paper now.
let's come up here and write these ratios out. We got AB. What should AB compare to?
AC.
AC. What should BC compare to?
CD.
Okay. And then the last one is AC
AD.
and AD. All right. Coming down here, we should have AB with
CB.
CB. We should have BC with
BD.
BD. And we should have then AC with
CB.
CD. And in the blue ones, we should have AC.
CB.
CD should go with
BD.
BD. And then AD will finish with
CBD.
CD. Okay? So here's the thing. We got those 9 ratios essentially. Okay? What I want you to understand is the scale factors that are developed from the black stuff are not going to be the same scale factor that is developed from the red stuff, which is not going to be the same scale factor that's developed from the blue stuff. Does that make sense to everybody? Even though the 3 triangles are similar, when I compare the big one, the overall one, to triangle. Okay, so I'm going to name these as triangle number 1 and triangle number 2 here. When I look at the big triangle, the overall one, and compare to triangle 1, I'm going to get a scale factor. Okay? Meaning then that I can take the big triangle, multiply it by that scale factor to reduce it to triangle number 1 size. Okay? Well, hopefully you understand that I cannot multiply by the same scale factor to reduce it to triangle 2 size. Okay? The big triangle and triangle 2 are going to have a different scale factor. And likewise, triangle 1 and triangle 2 are going to have a different scale factor. Okay? So I don't want to equate all 9 of those ratios, but they are all true for us in this problem in the event of trying to determine what these values of x and y are. So let me get rid of some stuff here and we'll try to work through this. We'll see. All right, so just trying to figure out what is true about this triangle with these proportions. What is AB's length? A to B, what would you call that?
AB would be 16 plus y.
Okay.
Or y plus 16 would be better.
Okay. What's AC's length?
20.
Okay. What's BC's length?
X.
And CD is 12. And then AC is 20.
AD 16.
Okay. Will that be enough to show you or to allow you to create a proportion, 2 proportions, solve for x and y? Yeah. Okay. I believe when you do that, you get x to be 15 and y to be 9, right? Okay. Now, some of you may not have used that relationship, or any of those relationships, because a relationship you might have used may have come from this red stuff. Okay, so let's kind of move this thing down here and do the red ratios. What would AB be? AB was 16 plus y, right?
16 plus y.
Okay. CB is x. BC is x, right? BD is y, and then AC is 20, and CD is 12 again. Okay. Now, are any of those red ratios existing up here in the black ones?
Yes. No.
No. Okay. We could maybe go through some proportion work to see that they might be. If I compare, think about, let's say I take that one and that one, and I equate them. Okay. Do they kind of look like these two?
Yeah.
But the x is in the x and the 20 in the wrong spots, aren't they?
Yeah.
But are we allowed to flip the means? All right. So they are there. All the proportions are there, but they might not be written exactly. So you might do a little bit of work to see that they're the same. But if you use any of these, do those? Can I pair these up to solve for x and y? It's going to be hard. You can, but it's going to be hard because this has x and y in it, right? Put it with 20 and 12, and we get an equation that has x and y in it. This has x and y in it. Compare it with 20 and 12, and we get another equation with x and y. So if I use these red ones, I actually have to use a system of equations to solve for x and y. It's doable, but it might be more work than necessary. If I come down here to the blue stuff, AC is 20. CB is x again. CD is 12. BD is y. AD is 16. And CD is 12. Okay. And looking at that one, those might be as easy, or maybe easier. Looking at the blue ones, those might be easier collectively than any of the other 6 ratios that we developed, right? Okay. But you should be able to use any of those as long as when you cross multiply, you're able to solve for a variable. If you have x solve for or y solve for, you should be good to go. All right. The reason I show it this way is, one, it's going to give you an appreciation for what we do later. Okay. Because if I ever come across this problem without any knowledge of further theorems, that's what you have to do. Okay. But two, some people might not have done all that and just kind of randomly or haphazardly chose some values, put them together, and got the right answer. I want you to know why you got that right answer. Okay? Or every time I do it, if I didn't do it this way with some of you in class, you might say, well, I did it this way. I used this ratio. Or I used this proportion. It's different than yours. Those are all the viable proportions and ratios you could use. All right? Does that make sense? You should get x to be 15 and y to be 9. And when you start plugging those things in then, okay, so if I've got Let me just clean a little bit of this stuff up here. If I had x to be 15 and y to be 9, okay, that makes this to be a 25 up here, doesn't it? So we have 25 over 20. Makes this here to be 15 over 12, doesn't it? Okay. So 25 over 20, what do they both have in common?
5.
5, so it goes to 5/4, right? Okay. What do these both have in common?
4. 3.
3. And it gives me
5 over 4.
5 over 4. What do these both have in common?
4.
4, and it gives me
5 over 4.
5 over 4. Okay. So that's verification that x was 15. Come down here, x was 15 and y was 9. Come down here, I get 25 right there. But now this is 15. X is 15, but y is 9. Reduce those. How many times is 5 going to both those?
5 over 3.
5 over 3. What about here?
5 over 3.
5 over 3. 5 over 3. Is the 5 over 3 the same as that 5 over 4? No. And that's what I was trying to show you guys, is that when I compare any of these triangles together, okay, the blue ratios, which would have been the comparison of the big triangle and then triangle ABC, not the blue one, the one at the top, I guess, all the way at the top of the page. Those ratios are not, or the scale factor is not the same as comparing the big triangle to triangle CDB on the right, okay? Which is then not the same ratio as comparing the two smaller triangles to one another. Because when I start doing this, just to save a little bit of time, these are all going to be they all divide by 5, don't they? So 4/3, 4/3, 4/3. Okay. So that's just something to pay attention to, that across the board, not all the scale factors are the same. But all triangles are similar. All right. But that is going to be very, very nice for us as we move on. Just to kind of show you real quick what we're going to do later with this is we're going to take that distance right there, which Blaze told us was an altitude, right? And it's going to go there and there. And then we're going to take the two parts down here, 16 and y, and I'll talk about why we do that later. And it's essentially because they developed some of those proportional ratios that we just created. If I get 144 is equal to 16y, divided by 16, and there's my 9. And that's such a faster way of getting that 9 than the approach that we had to do previously. Does that make sense? So hopefully it gives you an appreciation for that process here in a little bit. So I'm going to stop right there. And we got about 5 minutes here, but